In 1957, an experiment cooled a sample of metal to within 0.003 of a degree above absolute zero. The temperature alone was severe. The result was harder. What that experiment showed is that the universe distinguishes left from right. The mirror image of nature is not the same as nature itself. That result broke an assumption physicists had carried for centuries, that reality was symmetric, that a left-handed universe and a right-handed universe were interchangeable. They were not. Once that assumption fell, a stranger question replaced it. If the visible universe is asymmetric, could there be a hidden universe that completes the symmetry? Could there be a reflection of reality somewhere, invisible, untouchable, but real? For 70 years, that question has driven a quiet line of physics. Mirror matter, hidden sectors, time-reversed cosmologies, multiply connected geometries in which the same primordial light returns to us along different paths. Each describes a different way the universe might possess a reflection. Each shares one disturbing feature. The reflection, if it exists, does not contain an ordinary visible version of you. This video examines the science behind that claim. By the end, you will understand the Wu experiment that broke parity, the mirror sector hypothesis that emerged from it, the CPT-symmetric universe across the Big Bang, and the cosmic topology proposals that suggest space wraps around on itself. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Begin with something so ordinary that it is almost impossible to notice. You stand in front of a bathroom mirror. You raise your right hand. Your reflection raises its left. You comb your hair. You tie a tie. You adjust a collar. And every motion is reproduced but reversed. The image is convincing because the rules of the everyday world appear to be symmetric. A clock would tick the same way if the universe were flipped. A glass of water would fall the same way. A pendulum would swing the same way. For 3 centuries of classical physics, that intuition was treated as obvious. Nature, it was assumed, did not care whether reality was wired left-handed or right-handed. The mirror image of physics was physics. This belief had a formal name. It was called parity conservation. In the language of theoretical physics, parity is the operation that flips space coordinates. The expression is simple. P maps the point at coordinates x, y, z to the point at coordinates -x, -y, -z. Every position is sent through the origin to its mirror partner on the opposite side. If the laws of physics are unchanged after this operation, parity is conserved. If they are changed, parity is violated. For most of physics, the laws were unchanged. Gravitation respected parity. Electromagnetism respected parity. The strong nuclear force respected parity. The mirror image of every known process appeared to be another valid process, indistinguishable in its behavior from the original. But there was one corner of physics where the situation had not been carefully tested. The weak nuclear interaction, the force responsible for certain types of radioactive decay, had been studied since the 1930s without a direct, rigorous parity test. By the mid-1950s, theoretical physicists had begun to notice that certain particle decays appeared to be misbehaving. Two different particles, called the theta and the tau, had identical masses, identical lifetimes, and identical electric charges, yet decayed into final states with opposite parity. Either they were two different particles that happened to share every measurable property, or they were the same particle decaying into final states that should not coexist if parity were conserved. In 1956, two theoretical physicists, Tsung-Dao Lee and Chen-Ning Yang, surveyed the experimental literature carefully. Lee had been born in Shanghai on the 24th of November, 1926. Yang had been born in Hefei on the 22nd of September, 1922. Both had moved through the upheavals of mid-century China and emerged as senior figures in American theoretical physics by their early 30s. What Lee and Yang concluded was, on its face, a modest claim. They said that the assumption of parity conservation in the weak interaction had never been directly tested. They proposed concrete experiments by which it could be tested. One of those experiments involved a sample of cobalt-60 polarized at extremely low temperatures in a magnetic field, with electrons emerging from beta decay measured against the direction of nuclear spin. The proposal landed in a community that mostly expected the experiments to confirm the symmetry. Even Wolfgang Pauli, one of the founding figures of quantum mechanics, was reported to have said that he could not believe nature would be a weak left-hander. The experimental work was carried out by Chen-Shung Wu, an experimental physicist at Columbia University, who had been born in 1912 in eastern China, and who had built one of the most rigorous experimental programs in the field. Wu collaborated with researchers at the National Bureau of Standards in Washington, including Ernest Ambler, Raymond Hayward, Dale Hoppes, and Ralph Hudson, because they had access to the cryogenic apparatus needed to cool the cobalt sample to the temperatures the experiment required. The setup was demanding. The cobalt-60 source was prepared as a thin layer, only 50 micrometers thick, about 0.002 of an inch, deposited on the surface of a paramagnetic crystal. The crystal was cooled by adiabatic demagnetization to a temperature of approximately 0.003 Kelvin, 0.003 of a degree above absolute zero. A magnetic field of about 2.3 Tesla, equivalent to about 23,000 Gauss, was used to polarize the cobalt nuclei so that their spins all pointed in the same direction. A beta decay scintillation counter was placed about 2 centimeters above the source, about 0.79 inches, connected through a 120 centimeter lucite light pipe, about 47.2 inches, to bring the scintillation light to a photomultiplier outside the cryostat. Picture the scene. A small disk of cobalt sitting in a chamber colder than deep space. A magnetic field locking the nuclei into alignment. Detectors waiting in the surrounding apparatus to record the direction in which the emitted electrons travel. The question being asked was straightforward. If parity is conserved, the electrons should be emitted equally in both directions along the spin axis, as many heading toward the north pole of the magnetic alignment as toward the south. If parity is violated, one direction will be preferred over the other. The experiment was a left versus right ballot, conducted at a temperature where thermal disorder had been almost entirely silenced. The result came in late 1956 and was confirmed in early 1957. Electrons from the beta decay of cobalt-60 emerged preferentially opposite the direction of the nuclear spin. The asymmetry was unambiguous. Translated into the formal language of beta decay physics, the angular distribution of the emitted electrons was described by an expression of the form W of theta proportional to 1 plus A times V over C times cosine of theta. In words, the probability of emitting an electron at angle theta to the spin axis depends on that angle, with a coefficient A that captures the asymmetry, and a factor V over C that gives the electron speed relative to light. If parity were conserved, A would have been 0. It was not 0. The mirror image predicted the same number of electrons emitted in each direction. The actual experiment showed otherwise. What does it mean that the universe, in its weak interactions, is not the same as its mirror image? It means that there is a built-in handedness to fundamental physics. It means that the rules governing certain particle decays distinguish left from right at the deepest level we can measure. It means that the naive picture, the picture in which nature does not care which way around the universe is wired, is wrong. Within a year of Wu's result, in 1957, Li and Yang received the Nobel Prize in Physics for their proposal. Yang gave the Nobel lecture titled "The Law of Parity Conservation and Other Symmetry Laws of Physics." Wu, despite having led the experimental work that turned the proposal into discovery, did not share the prize, a fact that historians of physics have continued to examine and reassess in the decades since. This is the part that stays with me. Not the temperature, although the temperature was severe. Not the apparatus, although the apparatus was elegant. What stays is the proportion. A 50 micrometer layer of cobalt, cooled almost to absolute zero, exposed an asymmetry baked into the structure of reality. A laboratory of cubic meters uncovered a left-handedness in the universe at scales no microscope could resolve. The smallness of the sample is the point. You did not need to look further out to see it. You needed to look closer in. The Wu experiment did more than answer a technical question. It rearranged the landscape of fundamental physics. The naive mirror image, the picture in which everything reflects without consequence, was retired as a description of nature. Parity, which had been treated almost as a universal symmetry on the level of energy or charge conservation, became a property that some forces respected and others did not. Electromagnetism respected it. Gravitation respected it. The strong force respected it. The weak force violated it. The first reflection of reality, the simple one, was broken. But theoretical physicists are restless. The asymmetry uncovered by Wu was uncomfortable for a community that had grown accustomed to symmetry as a guiding principle. If parity was violated in our visible sector, the question became whether the symmetry could be restored at a deeper level. there might exist another sector of particles, another set of forces, another piece of physics in which left and right were swapped, so that the combined description of the visible and hidden sectors recovered the symmetry that the visible sector alone had lost. The first serious answer came in 1966 from three Soviet physicists. Igor Kobzarev, Lev Okun, and Isaac Pomeranchuk proposed what they called mirror particles. The idea was austere. Suppose that for every particle in our sector, every electron, every proton, every neutron, every photon, every neutrino, there exists a mirror counterpart in a separate sector. The mirror particles obey the same physics as ours, but with handedness reversed. Where our weak interaction prefers left-handed particles, the mirror weak interaction prefers right-handed mirror particles. Taken together, the visible sector and the mirror sector restore the parity symmetry that either sector alone violates. Notice what this proposal does. It does not deny the result of the Wu experiment. It accepts the asymmetry as established. It then asks whether the asymmetry might be a consequence of incomplete description, whether what we call the world might be only one half of a wider physical structure that, when seen whole, is symmetric. In the language of the proposal, the mirror sector is an exact partner of the visible sector. The mirror has its own electrons, its own protons, its own atoms, its own chemistry, its own forces. It is not a metaphor, it is a postulated physical structure. And it is dark to our telescopes not because it is far away, not because it is hidden behind a barrier, but because mirror photons interact only with mirror matter, and ordinary photons interact only with ordinary matter. The two sectors share a universe, but do not share light. The Kobzarev, Okun and Pomeranchuk paper was a hypothesis, not a discovery. They did not have evidence for the mirror sector. What they had was a structural proposal, a way of asking whether parity, having been violated in our visible sector, might still be a deep symmetry of nature once the full theory was written down. Lev Okun, in a much later review published in 2006, described mirror particles and mirror matter as a hypothetical hidden sector of particles and interactions designed to compensate the mirror asymmetry of weak interactions. That phrase, to compensate the mirror asymmetry, captures the ambition. The asymmetry we observe is not denied. It is restated as a partial view of a larger symmetric structure. We will return to this assumption later. The mirror sector, in the form first proposed in the 1960s and developed through the 1990s and 2000s, is not free of explanatory costs. It restores symmetry by doubling the particle content of the universe. It introduces a new sector that interacts with ours primarily through gravity and possibly through extremely weak portal couplings. It depends on assumptions about the relative temperatures, abundances, and histories of the two sectors. Each of those assumptions will return for examination in due course. For now, set them aside. The point in this part of the story is that the mirror sector idea was not a fringe proposal. It came from senior physicists. It engaged with the implications of the Wu result. And it laid down the conceptual framework for what would later be called hidden sector physics. The 1966 paper opened a door. It did not walk through it. The next decisive step came 25 years later. In 1991, three physicists, Robert Foote, H. Liu, and Raymond Volkas, published a paper that took the mirror idea further. They argued that parity could be an exact, unbroken symmetry of nature if the standard model of particle physics were enlarged to include a mirror copy with its own forces and its own mirror particles. In the Foot, Lou and Volkas formulation, ordinary electrons, protons, neutrons, photons and neutrinos have mirror counterparts, written E', P', N', gamma prime and nu prime, that interact with each other through mirror versions of the electromagnetic and weak forces. The mirror counterparts do not normally show up in ordinary detectors because the visible and mirror sectors are largely decoupled. The connection between them is gravitational. Anything else is, at most, very weak. The Foot, Lou and Volkas paper was a more concrete construction than the original Kobzarev, Okun and Pomeranchuk proposal. It showed, in detail, how a mirror sector could be added to the standard model in a mathematically consistent way. It made parity an exact symmetry of the enlarged theory. It allowed mirror chemistry, mirror nuclei, mirror atoms, even, in principle, mirror stars and mirror structures of some kind, all hidden behind the gravitational-only interaction with our sector. This is where the question of reflection takes on a sharper edge. Imagine for a moment what a mirror world like this would look like if you could see it. The mirror sector is not a movie set. It is not a parallel Earth waiting to be visited. It is a separate set of particles, obeying the same kinds of rules, occupying the same universe, but invisible to ordinary light. If a mirror galaxy existed in the sky, no telescope tuned to ordinary photons would detect it. A mirror star, however hot, would emit only mirror photons, and those photons would not interact with the mirror of your camera or the rod and cone cells of your eye. The mirror world would be everywhere our ordinary world is, in the sense that mirror gravity reaches everywhere ordinary gravity reaches, and yet completely invisible. There is something austere about this picture that distinguishes it from popular ideas of parallel worlds. The mirror sector in this formulation is not an alternate Earth where you exist as a different person making different choices. It does not promise a duplicate of your life lived backwards. The reflection is a reflection of physics, not a reflection of biography. The mirror sector contains its own particles, its own dynamics, its own structures, and there is no general reason to expect that any of those structures correspond to recognizable versions of you, or of anything you would call yourself. The theory of evolution is sometimes invoked to suggest that, given enough time and any sufficiently rich substrate, life like ours will emerge. We will examine that claim in a different context later. For now, simply note what the mirror sector hypothesis does and does not require. It requires the existence of mirror particles obeying the same kinds of laws as ours. It does not require that mirror history retrace ours. It does not require that mirror chemistry produce mirror biology. It does not require that mirror biology produce a mirror version of you. The reflection in this formulation is a reflection of physics, and a physical reflection of laws need not contain any ordinary visible observer at all. That is the key fact to hold in mind as we move into the next section. The reflection is not what intuition expects. Let us turn now to the cosmology of the mirror sector, and to a series of refinements that, on close inspection, raise questions we will need to return to. The most important figure in mirror cosmology in the modern era is Zurab Bereziani, who developed the idea of a mirror world that began at a different temperature than ours. In Bereziani's framework, the mirror sector is not a copy of our sector running in parallel. It is a partner that started colder, evolved more slowly, and produced a different cosmic history. This is not a cosmetic adjustment. It is essential to making the mirror sector compatible with what we already know about the early universe. Here is why. Cosmologists measure something called the effective number of relativistic species, denoted N. Effective. It is a way of counting how many particles were behaving like radiation at the time the cosmic microwave background formed. The radiation density during that epoch is captured by the formula ρ radiation equals 1 plus 7/8 times 4/11 to the 4/3 power times N effective, all multiplied by the photon density ρ gamma. The variables in that expression are simple to describe. N effective counts effective relativistic species. Rho gamma is the photon energy density. The formula is standard early universe cosmology bookkeeping. The point of mentioning it is this. If a mirror sector existed, and if it had the same temperature as our sector, it would contribute another set of relativistic species at every epoch. Mirror photons, mirror neutrinos, mirror radiation in general. This would change N effective. The cosmic microwave background and primordial nucleosynthesis are extraordinarily sensitive to N effective. A full thermal mirror copy of our sector sharing our temperature would push these observables out of agreement with observation. A symmetric mirror world, naively constructed, would conflict with measurements that have been refined for decades. Bereziani's solution was to assume that the mirror sector began colder than ours. A colder mirror sector contributes less to the radiation density. Its stars, its chemistry, its structure formation all proceed on a different schedule. It can still exist, it can still gravitate, it can still, in principle, supply much or all of the dark matter inferred from observations. Gravitational lensing, galaxy rotation curves, cluster dynamics, the cosmic microwave background. But it does so only if the cosmic temperature ratio between the visible and mirror sectors is tuned to a particular range. Too hot, and the mirror sector ruins early universe cosmology. Too cold, and the mirror sector cannot produce enough dark matter. Keep this number in mind. We will need it. This brings us to a broader frame. The mirror sector is one example of a more general idea called a hidden sector. In physics terminology, a hidden sector is a set of particles and interactions that does not couple to the standard model at the level of ordinary forces, electromagnetism, the strong force, the weak force, but may couple gravitationally or through extremely small additional couplings called portals. The hidden sector framework is not specific to mirror matter. It encompasses many possibilities, of which mirror matter is one historically important example. The reason hidden sectors have become a major research direction is that the mainstream picture of the universe contains a giant unexplained ingredient called dark matter. The 2024 Particle Data Group review states that dark matter constitutes 26.4% of the universe's critical density and 84.4% of its total matter density. The universe's critical density itself is given by the formula ρc equals 3h squared divided by 8 pi g, where h is the Hubble expansion rate and g is the gravitational constant. The percentages quoted are fractions of that density. When we say that dark matter accounts for 26.4% of the cosmos, we are reporting a measured share of the total energy budget of the universe, not a speculative placeholder. The evidence for dark matter is gravitational and observational. Galaxy rotation curves show stars in the outer regions of galaxies orbiting too quickly to be held by the mass that ordinary light reveals. Cluster dynamics show galaxies bound together by more gravity than visible matter can supply. The cosmic microwave background fits a model in which a non-luminous matter component dominated structure formation in the early universe. Gravitational lensing, the bending of light by mass, reveals that the bending is too strong to be explained by visible matter alone. The deflection of light by a point mass m is given, in the classical limit, by the formula alpha equals 4gm divided by c squared b, where alpha is the deflection angle, b is the impact parameter, and c is the speed of light. When astronomers measure the bending of light by a galaxy or a cluster, they back out the mass through that formula, and the inferred mass exceeds the visible mass by a wide margin. A specific observation will help anchor what dark matter means. Picture the Bullet cluster, located about 3.8 billion light-years away, roughly 3.6 times 10 to the 22nd kilometers, or 2.2 times 10 to the 22nd miles. The Bullet cluster is not a single object. It is two galaxy clusters that have collided, and their hot gas has been observed by the Chandra X-ray Observatory, while their total mass has been mapped by gravitational lensing of background galaxies. What astronomers see is striking. The hot X-ray gas, which contains most of the ordinary matter, has been left behind in the center of the collision, where the two gas clouds slammed into each other and stalled. The lensing inferred mass, however, has continued forward with the galaxies. The mass and the gas are physically separated. This is what dark means in modern astrophysics. It does not mean nothing. It means matter that gravitates without emitting visible light. The Bullet cluster shows two distinct distributions, one of light-emitting gas, one of gravitating mass, and the two are not in the same place. Whatever supplies that gravitating mass passed through the collision while the gas was decelerated. For more than 2 decades, the Bullet cluster has stood as one of the strongest visual anchors for the case that there is something gravitating in the universe that ordinary matter cannot account for. What the mirror sector hypothesis offers is a candidate identity for that missing matter. If the universe contains a hidden sector of mirror particles that gravitate but do not emit ordinary light, those mirror particles could in principle constitute the dark matter we infer from the bullet cluster, from rotation curves, from lensing, from the microwave background. This is the connection that has kept mirror matter alive as a research program. It is not merely a structural curiosity from the parity violation literature. It is a candidate explanation for the largest unsolved component of the cosmic energy budget. But, and this is the foreshadowing that will return in due course, mirror dark matter requires the temperature asymmetry we just described. It requires that the mirror sector began colder. It also typically requires very small portal couplings between the visible and mirror sectors to avoid violating the constraints that hot dark matter or strongly interacting dark matter scenarios run into. The mirror sector restores parity, supplies dark matter, and stays hidden, but only if a series of cosmological numbers cooperate. The logic here depends on something we have not yet tested. The most studied of these portal couplings is called kinetic mixing. The idea was developed in the 1980s and 1990s in a series of papers, most famously associated with the physicist James Oldham, whose 1986 paper laid out the theoretical framework. In its simplest form, kinetic mixing is a tiny term in the equations of motion that couples an ordinary photon to a hidden sector photon. The hidden sector photon is sometimes called a dark photon. Through kinetic mixing, dark photons acquire a small effective interaction with ordinary charged particles, small enough that the dark photon has not been seen, large enough that, if it exists, it could in principle be detected with the right experiments. The mathematical expression for kinetic mixing is compact. Written as a Lagrangian term, it reads L mix equals minus epsilon over 2 times F mu nu times F prime mu nu. In words, the ordinary photon's field strength tensor, called F mu nu, is multiplied with the hidden sector photon's field strength tensor, called F prime mu nu, and the product is multiplied by a small mixing parameter epsilon divided by 2, with an overall minus sign. The variables tell the story plainly. F mu nu is the ordinary electromagnetic field. F prime mu nu is the hidden sector electromagnetic field. Epsilon is a small number that controls the strength of the crosstalk. If epsilon is 0, the two sectors are completely decoupled. If epsilon is large, the crosstalk is strong and would have been seen long ago. The physically interesting region is epsilon very small but not 0. Small enough to evade existing constraints, large enough to remain potentially detectable. What makes this formulation important is that it gives the reflection a graded visibility. A perfectly gravitational mirror sector would be effectively invisible except through large-scale gravitational effects. A weakly mixed sector, by contrast, could leave traces in laboratory experiments. Orthopositronium decays. The decay of a bound state of an electron and a positron could exhibit anomalies if mirror states existed and could be reached through the mixing. Direct detection experiments, underground detectors looking for dark matter-induced recoils, could see signatures of mirror-electron interactions. Fixed target searches and particle colliders could produce dark photons through the mixing and detect them through missing energy signatures or unusual displaced decays. Each of those experimental approaches has been tried. None has produced a confirmed signal. The Large Underground Xenon experiment, known as LUX, conducted a direct test specifically aimed at the mirror dark matter scenario. Using 95 live days of data with 118 kilograms of liquid xenon, LUX searched for the recoil signatures predicted if mirror electrons were scattering off ordinary atoms through kinetic mixing. The 2020 analysis reported no evidence for such a signal and significantly tightened the allowed range of the kinetic mixing parameter for that specific mirror dark matter interpretation. The LUX result is one example of a much broader pattern. The CMS collaboration at the European Organization for Nuclear Research, better known as CERN, has reviewed dozens of dark sector and dark matter searches across years of data. The ATLAS collaboration continues to search for semi-visible jets, emerging jets, displaced decays, and other hidden sector signatures. The ATLAS dark sector summary phrasing has become standard across the literature. After detailed analysis, no significant excess above the expected background is observed. The Particle Data Group review repeats the same finding across the broader program. No Large Hadron Collider dark matter signal has been observed so far. A new facility called SHIP, which stands for Search for Hidden Particles, was advanced toward approval at CERN in 2024. SHIP is designed for feebly interacting, long-lived particles and includes a 50-meter decay chamber. The length is not a vanity. It is a calculated bet on what hidden sector physics, if it exists, looks like. Particles produced by ordinary collisions decay quickly. The proposed hidden sector particles, by contrast, are expected to travel macroscopic distances before decaying back into something detectable. Distances measured in meters rather than nanometers. A 50-meter chamber is the reach SHIP needs to catch a decay, in flight, between production and disappearance. The facility is scheduled to begin in the early 2030s. Outside the laboratory, the cosmological constraints on hidden sector physics are tightening as well. The Euclid Space Telescope, launched on the 1st of July 2023 by the European Space Agency, was designed to map the geometry of the dark universe. Its first data release in March 2025 previewed deep fields containing approximately 26 million galaxies, the most distant of them lying beyond 10.5 billion light-years. The release covered 63.1 square degrees of sky in its initial Q1 package, a small fraction of what Euclid will eventually map. For hidden sector physics, Euclid matters because future weak lensing maps and structure growth measurements will further constrain dark sector dark matter possibilities, even where they are not specifically targeting mirror matter. The mass distribution of the universe is being measured at scales and statistical sensitivities that put new pressure on every model claiming to account for the missing matter. Picture the experimental landscape as it stands. Underground, in the Lux detector and its successors, xenon waits patiently for the recoil of a mirror electron that may never come. At the surface, in the cathedral-sized halls of CMS and Atlas, protons collide millions of times per second, and detectors examine the debris for the missing energy or unusual jets that would betray a hidden particle. Above the atmosphere, Planck's archive holds the most detailed cosmic microwave background map ever assembled, scanned for matched circles that have not been found, and Euclid begins charting the dark universe geometry in unprecedented detail. From three different fronts, direct detection, collider production, and cosmological observation, physicists are pushing the reflection models into ever narrower corners of viable parameter space. The reflections, if they exist, have grown progressively quieter. They have not become louder. What does it mean that decades of increasingly sensitive experiments have searched for hidden sector signatures and found none? It does not mean the hidden sector does not exist. It means that, if it exists, the couplings are small. The mirror sector hypothesis remains alive. It has not been ruled out, but it survives by retreating into ever smaller corners of the allowed parameter space. Each null result is a constraint on how strong the connection between our sector and the mirror sector can be. Notice what this requires us to accept. A reflection of reality whose presence is registered only by what is not observed. We have spent some time on the mirror matter idea because it is the historically central proposal and because it is conceptually rich. But there are other reflections to consider, reflections that are not built on hidden particles at all. The next one is built on time. In 2018, three physicists, Latham Boyle, Kieran Finn and Neil Turok, proposed a model in which the universe after the Big Bang is the CPT image of the universe before it. CPT stands for the combined operation of charge conjugation, parity, and time reversal. Charge conjugation, denoted C, replaces particles with their antiparticles. Parity, denoted P, flips spatial handedness. Time reversal, denoted T, runs the clock backward. The combined CPT operation is written as CPT equals C times P times T. The CPT theorem in quantum field theory states that any physically reasonable theory should be invariant under the combined CPT operation, even if it is not invariant under any of the three operations separately. The Boyle, Finn and Turok proposal takes this very seriously. Rather than treating the Big Bang as a singular first moment of one-sided time history, the proposal treats the Big Bang as a boundary between a universe and an anti-universe. Our side of the bang has the temporal arrow we experience, the matter content we observe, and the handedness of weak interactions we measure. The other side of the bang has the reversed arrow, the swapped matter and antimatter content and the opposite handedness. The two halves are mathematically symmetric across the boundary in the language of conformal time. The structure that supports this proposal is a particular form of the cosmological metric. The flat case of the standard cosmological metric in conformal time can be written as ds squared equals a squared of eta times the quantity d eta squared minus dx squared. The variables tell what the equation describes. The interval ds is the space-time interval between two events. The function a of eta is the scale factor, the size of the universe at conformal time eta. The coordinates x are co-moving coordinates that move with the cosmic expansion. The conformal time language is well suited to the Boyle, Finn and Turok proposal because it allows the universe to be described symmetrically across the bang. What the model claims is striking. It claims that dark matter can be accounted for using only the standard model plus right-handed neutrinos. It predicts one stable, heavy right-handed neutrino with a mass of 4.8 times 10 to the 8th giga-electron volts. It predicts that the lightest neutrino in our sector is massless. It predicts that the light neutrinos are Majorana, meaning they are their own antiparticles. It predicts that the model's mechanism does not produce primordial, long-wavelength gravitational waves of the type that simple inflationary models tend to generate. The temptation, when describing this model, is to picture another galaxy floating somewhere in space, a second visible Milky Way that mirrors ours. That picture is wrong. The CPT-symmetric universe is not somewhere you could go. It lies on the other side of the Big Bang in conformal time. The reflection here is not spatial. It is not a mirror sector in the same universe. It is a partner cosmology across a boundary in time. If the proposal is correct, the reflection of our universe runs backward in some appropriate sense, contains the CPT conjugates of our particles, and is causally disconnected from us by the structure of the boundary itself. What does it mean that the reflection is not elsewhere, but elsewhen? It means that even in physics, the most austere senses of the word reflection have stretched far beyond ordinary intuition. Common sense imagines a reflection as an image of you somewhere else doing what you do, or doing the opposite of what you do. The CPT proposal does not offer that. It offers a cosmologically symmetric extension of the universe, a mathematical structure that completes a temporal symmetry across the bang. There is no second you in that picture in any everyday sense. Notice what this requires us to accept. The CPT-symmetric proposal is a specific framework. It depends on a specific mechanism for generating the mass of the right-handed neutrino. It depends on a specific assumption about the absence of primordial long-wavelength gravitational waves. It depends on a specific symmetry at the boundary. None of these has been confirmed. The neutrino properties the proposal predicts sit at the edges of what neutrino experiments are capable of measuring. The absence of long-wavelength gravitational waves cannot be turned into a positive test of the model. It is the absence of an effect which is harder to verify than its presence. The proposal is intriguing precisely because it is bold, but it is not established. We will return to this elegance later. There is a third kind of reflection that deserves its own treatment, and it is stranger still. It is built not from hidden particles, not from time, but from the geometry of space itself. The proposal goes by the name cosmic-topology. The classical formulation came in 1998, in a paper by Neil Cornish, David Spergel, and Glenn Starkman. Topology, in physics, refers to the global properties of a space, properties that survive continuous deformations of the space itself. Two spaces with different topologies cannot be smoothly turned into one another. A sphere and a donut have different topologies. So do a flat infinite plane and a flat finite torus. The local geometry of a space, how distances and angles work near any point, does not by itself determine the topology. You can have a space that is locally flat but globally finite, locally curved but globally infinite, or locally any combination of geometric properties wrapped into any of several topological possibilities. The Cornish, Spergel, and Starkman proposal noted something simple but profound. If the universe is finite, and if the size of the fundamental domain, the smallest piece of space that captures the topology, is smaller than the co-moving distance to the last scattering surface, then the same surface of last scattering can be observed along multiple lines of sight. The surface of last scattering is the spherical shell from which the cosmic microwave background photons we receive today were originally emitted when the universe was about 375,000 years old. If the universe is multiply connected, meaning that going far enough in one direction brings you back along another, then the shell of last scattering wraps around the universe and intersects itself. Where the shells intersect, they trace out circles on our sky. These circles would carry matched temperature patterns in the cosmic microwave background. The same primordial patch, seen from two different directions, would produce two circles that should look statistically alike. Cornish, Spergel, and Starkman called this the matched circles test. It was a way of looking for cosmic topology by searching the cosmic microwave background for repeated patterns. Picture this carefully. Imagine standing in a room whose walls are mirrored. Not perfect mirrors, but a finite cubical room with the property that walking through any wall brings you back through the opposite wall. The geometry inside the room is ordinary, but its global structure repeats. Now look at any object in the room. You can see it directly in front of you. You can also see it through the wall behind, in front of, beside, and above you, because each wall opens onto a copy of the room. The object appears at multiple angles. The cosmic topology proposal applies an analogous logic to space-time. If the universe has the global structure of a finite, multiply connected space, then primordial structures should be visible from multiple directions, with the matched circles in the microwave background being the most direct observable signature. The proposal was sharpened in 2003 by Jean-Pierre Luminet and collaborators, who suggested a particular kind of finite, positively curved space as a candidate global topology. The space they proposed is called Poincaré dodecahedral space. It is a quotient of a three-sphere by a particular discrete group of rotations, and it has the property that walking in a straight line in certain directions eventually brings you back to your starting point along a particular pattern. Luminet's group claimed that this topology could fit certain weak, large-angle correlations seen in the early cosmic microwave background data, and predicted a total density parameter of approximately omega 0 of about 1.013, a slight positive curvature. In narrative terms, the dodecahedral universe is the cleanest visual route to a hall of mirrors metaphor for cosmic topology. If space wraps around with the symmetry of a dodecahedron, the lines of sight back through the universe would produce a pattern of repeated views in highly specific geometric configurations. You would not be seeing copies of yourself, you would be seeing copies of cosmic structures, primordial in origin, repeated by the geometry of space. Then came Planck. The Planck satellite, launched on the 14th of May 2009 by the European Space Agency, was the most sensitive cosmic microwave background mission ever flown. It carried two instruments, the low-frequency instrument and the high-frequency instrument, spanning frequency bands from 30 to 857 GHz, with angular resolution as fine as about 5 to 10 arc-minutes across the bands. Planck took everything WMAP had achieved, the earlier mission launched on the 30th of June 2001 and operating until 2010, observing in 5 microwave bands at 23, 33, 41, 61 and 94 GHz, with about 13 arc-minute resolution, and refined it with a precision that allowed serious topology searches to be performed. Planck's 2015 topology analysis reported no detection of a compact topology below the diameter of the last scattering surface. For the simplest cubic torus topology, the analysis found that the in-radius, the radius of the largest sphere fitting inside the fundamental domain, must be greater than 0.97 times the co-moving distance to the last scattering surface, at 99% confidence, when the analysis used polarization-based matched circle searches. For a slab geometry, the corresponding bound was in radius greater than 0.56 times that distance. Translated into physical terms, the cosmic topology proposal had been pushed to scales at or beyond the size of the observable universe. The simple, multiply connected models that had once been seriously discussed were no longer favored by the data. The matched circles, if they exist at all, are at scales that put them outside the reach of straightforward detection. Luminet himself, in later reviews, acknowledged that Planck data is consistent with the simplest, nearly flat, infinite cosmological model, although he continued to argue that some more complex topologies remain observationally consistent at some level. The status of cosmic topology is therefore not ruled out, but no positive detection, with constraints substantially tightened. What does it mean that the most carefully designed test of cosmic topology in human history has produced no detection? It does not mean the universe is infinite. It means that if the universe is finite and multiply connected, it is so on scales that approach or exceed the size of the observable cosmos. The matched circles, if they exist, are out where light from the early universe has barely reached us. The reflection in the geometry of space, like the reflection in the mirror sector and the reflection across the Big Bang, has retreated to a corner where it cannot easily be seen. We have now surveyed 3 proposals for what physics could mean by a reflection of reality. The first, mirror matter, posits a hidden sector of particles whose handedness reverses ours and whose interactions with our sector are gravitational and possibly very weakly electromagnetic. The second, the CPT-symmetric universe, posits a partner cosmology across the Big Bang in conformal time, related to ours by the combined operation of charge conjugation, parity, and time reversal. The third, cosmic topology, posits a multiply connected geometry of space such that the same primordial structures can be observed along multiple lines of sight. Let us pause here. Take a moment. Each of these proposals has been developed by serious physicists in serious journals with serious mathematical machinery. Each of them has measurable predictions. Each of them has been subjected to experimental tests. Each of them survives, in the technical sense that they have not been ruled out, but each of them lacks a confirmed positive detection. And each of them shares a feature that takes some time to absorb. The reflection they describe, if it exists, does not contain you. There is no ordinary, visible mirror Earth, mirror Milky Way, mirror civilization waiting to be detected on the other side of any of these models. The mirror sector posits parallel particles, not parallel biographies. The CPT-symmetric universe posits a temporal partner across a boundary, not a spatial neighbor. The cosmic topology proposals posit repeated lines of sight, not repeated lives. The reflection is real in a series of austere physical senses. It is not real in the sense that everyday intuition wants. The reflection of reality, as physics has gradually mapped it, has stretched the meaning of the word reflection until it almost no longer fits the bathroom mirror image we started with. This is the part that, when I first understood it, changed how I thought about the question. The popular science framing of mirror universes, parallel worlds, and other cosmologies often imports the bathroom mirror picture by default. The physics, examined carefully, does not. The reflection that physics describes is a structural feature of laws, particles, time, or geometry. Where common sense expects a duplicate of you, physics offers a different particle sector, a temporal partner, or a topological repetition of patterns in the early universe. These are not the same thing as a second you. What does it mean that physics has built three different reflections of reality, none of which contain an ordinary visible duplicate of any observer in our sector? It means that for all the structural symmetries the universe might possess at deep levels, the symmetry does not extend to producing a redundant copy of conscious life. The reflection, if it exists, is austere. It is a reflection of laws, not of biographies. We have now established the science. The Wu experiment broke parity. Mirror matter and hidden sector models attempted to restore symmetry through a doubled particle content. Bereziani's cosmology made the mirror sector a candidate for dark matter while requiring it to be colder than ours. Holdom's kinetic mixing portal allowed graded visibility through a small parameter epsilon. The Lux experiment and the broader CMS and Atlas programs have constrained but not eliminated such models. The Boyle, Finn and Turok CPT-symmetric universe proposed a temporal partner across the Big Bang. The Cornish, Spergel and Starkman matched circles test, sharpened by Luminet's dodecahedral proposal, sought topological repetitions in the cosmic microwave background. Planck's 2015 analysis reported no detection of compact topologies below the last scattering scale. These are the facts. We have presented them as the literature presents them. We have not yet examined what they mean. Earlier in this video, I told you we would return to a series of questions. We will do so now. The questions are these. Why does the mirror sector require a thermal asymmetry? Why does the kinetic mixing parameter epsilon need to sit in a tiny, observationally allowed window? Does symmetry across the Big Bang explain existence, or does it explain only one possible pattern within existence? And how often do sweeping metaphysical conclusions get hung on models still awaiting positive detection? These are not idle questions. They go to the heart of what these models do, what they do not do, and what claims can rationally be drawn from them. There is a popular line of interpretation, sometimes drawn loudly, sometimes drawn quietly, that reflection of reality physics shows that the universe is self-explaining, that no creator is needed, that fine-tuning is illusory, that the deepest questions of existence have already been answered or will soon be answered by the next iteration of theory. Let us examine that interpretation carefully. The first claim to examine is this. Some popular interpreters of hidden sector physics argue that the existence of mirror matter, or a CPT-symmetric universe, shows no creator is needed, that physics has found, or is on the way to finding, a self-sufficient mathematical structure that requires no further explanation. The argument is rarely stated this baldly in technical papers. It appears more often in commentary, in popularization, and in the metaphysical extrapolations that adhere to interesting physics like sediment to a stone. Let us take that claim in its strongest form. Suppose, for the sake of argument, that one of the reflection models is correct. Suppose mirror matter exists, or the CPT-symmetric universe is real, or cosmic topology is multiply connected. None of those facts entails that no creator is needed. The argument fails because of a category mistake at its core. The reflection models describe possible structures within a lawful cosmos. They do not explain why there is a lawful cosmos rather than no cosmos at all. The mirror sector hypothesis takes the standard model of particle physics and doubles its particle content. The CPT-symmetric proposal takes the standard cosmological metric and extends it symmetrically across the Big Bang. The cosmic-topology proposals take general relativity and impose particular global geometric conditions. In every case, the model presupposes laws, the same gauge symmetries, the same field equations, the same cosmological framework, and proposes a particular structural extension of those laws. None of the models explains why the laws exist. None of them explains why there are laws to extend. Consider what the mirror sector hypothesis actually requires. It requires the same standard model gauge structure to be replicated in a hidden sector. It requires the same kinds of gauge bosons, the same kinds of fermions, the same kinds of force-mediating interactions, with handedness reversed. It requires a cosmological history in which the mirror sector started colder. It requires portal couplings to be small enough to evade detection. It requires gravity to act on both sectors. Each of those requirements is itself a structural assumption, a piece of inherited mathematical and physical machinery that the model does not derive from anything more fundamental. When a popular interpreter says that mirror matter shows no creator is needed, they are saying that a model assuming gauge symmetry, the structure of quantum field theory, the existence of cosmological boundary conditions, and the inheritance of general relativity somehow demonstrates that no further explanation is required for any of these things. The claim does not survive examination. It conflates a structural extension with an ultimate explanation. It treats one possible pattern within existence as if it answered the question of why there is existence in the first place. A similar problem afflicts the popular framing of the CPT-symmetric universe. Boyle, Finn, and Turok wrote a careful technical paper proposing a specific symmetric extension across the Big Bang. The paper is mathematical and modest. It does not claim to solve the question of why there is a universe with these laws at all. The popular framing, however, sometimes leaps from "the Big Bang has a symmetric continuation" to "therefore, creation is just a boundary condition, and no creator is needed." This is precisely the leap the technical paper does not make. Consider what the symmetric continuation actually does. It treats the Big Bang as a boundary between two halves of a larger structure. The total structure, the universe and its CPT partner, is then taken as a self-consistent whole. But notice that the question of why this whole exists has not been answered. It has been moved. Where one might once have asked, "Why is there a universe?" one now asks, "Why is there a universe partner pair related by CPT?" The new question is not less profound than the old one. It is, if anything, more so. The model does not eliminate the question of existence. It restates it at a higher level of structural complexity. A locksmith examining a door can describe every tumbler and every spring. He can show you precisely how the bolt retracts when the right key is turned. He can produce a diagram of the entire mechanism. And then someone asks him, "Why is the door here?" He looks at his diagram. He looks at the door. He says, "I have not answered that question. I have only described how the door works." The CPT-symmetric proposal describes how a particular mathematical extension across the Big Bang could work. It does not address why such an extension exists at all. What does it mean that a mathematically elegant symmetry across the Big Bang has been mistaken for an answer to the question of existence? It means that, in the public reception of cosmology, mechanism has often been confused with origin. The two are not the same. A mechanism describes how something operates given that it exists. An origin explains why it exists at all. Physics, at its best, describes mechanisms with extraordinary precision. It does not describe origins of laws and existence in the same way, because origins of that kind are not the kind of thing physics measures. The materialist line of interpretation, taken to its logical end, runs into a self-inflicted difficulty here. If the response to "why is there a universe" is "the universe is its own answer because it has a symmetric continuation," then one has implicitly accepted that something has always existed in some sense, namely the symmetric universe partner pair. The materialist has accepted the existence of an eternal structure. The only remaining question is whether that eternal structure is unconscious mathematics with no further explanation, or whether it is itself an effect of an intelligent cause that is genuinely uncaused. Notice the move. The naturalistic response to the cosmological question accepts an eternal something without examining whether the something is the kind of thing that can stand on its own. The mirror sector, the CPT partner, the cosmic topology, each of these is a structured, lawful, finely arranged piece of physics. None of them has ever been observed to exist without a context of laws, fields, and constants. To take such a structure as an ultimate stopping point is to conclude that complex, lawful, finely arranged structures simply exist without explanation. It is to accept, as a brute fact, that the universe is the kind of place where law-bound mathematical structures exist on their own, with no further account required. This is not a stronger position than the alternative. The alternative, that an uncaused, intelligent cause underlies the lawful structure of reality, at least proposes the kind of thing that can plausibly be uncaused. An intelligent cause, by definition, is not built out of further physical components. It is not a mathematical structure that could have been otherwise. It is the source from which the lawful structure derives. The alternative positions an uncaused cause that has the right ontological character to be uncaused. The materialist positions an uncaused structure that has every appearance of being the kind of thing that requires explanation. You cannot have an infinite chain of dependent causes. If every cause requires a prior cause going back without limit, nothing ever begins, and we would not exist to ask the question. The chain terminates somewhere. The only honest question is what kind of thing the terminus is. The reflection models, considered carefully, do not push the terminus further back. They simply rearrange the structure within it. The second claim to examine is more subtle. Some popular interpreters argue that the kinetic mixing parameter epsilon, the tiny number that controls the crosstalk between the mirror sector and ours, is not an example of fine-tuning, but merely a parameter to be measured. This claim deserves close attention. When mirror dark matter is to be a viable candidate, the parameter epsilon must sit in a particular window. Too large, and the visible mirror coupling would have produced effects that have already been searched for and not found. Too small, and the mirror sector loses any laboratory signature, becoming empirically inert. The interesting region, the one that mirror matter advocates point toward, is the narrow band where epsilon is small enough to evade existing constraints, but large enough to be potentially detectable. Consider what this requires. The visible and mirror sectors must be coupled by exactly enough crosstalk to remain interesting. If the parameter were drawn at random from a distribution that allowed any value, the probability of it sitting in the narrow, viable band is, by every conventional accounting, very small. Defenders of mirror matter sometimes respond that the value of epsilon is determined by some deeper underlying physics, by the dynamics of whatever theory generates mirror sectors in the first place. That response, however, simply moves the fine-tuning question back a step. The deeper theory must itself be tuned to produce a value of epsilon in the right window. The puzzle is shifted, not resolved. Picture a combination lock with 26 dials. Each dial can be turned to any of an enormous range of values. The lock opens only when all 26 dials are set to specific values, not approximately, but precisely. The probability of hitting the right combination at random is so small that it has no useful analogy in human experience. But here is what makes the universe stranger than any combination lock. The dials were not turned by anyone we know. They appear to have been preset, set at values consistent with a viable, lawful, life-permitting structure. Mirror dark matter, when its parameters are examined, adds yet more dials to this lock. The temperature ratio between sectors, the kinetic mixing parameter, the relic abundance, the structure formation history, and each must sit within a narrow band for the model to be viable. This is the point at which the materialist response often invokes the multiverse. The argument, in its popular form, runs something like this. If there are infinitely many universes with random parameters, then some of those universes will happen to have the right values for life to exist, and we, of course, find ourselves in one of those. The fine-tuning is illusory, because the lottery has been played infinitely many times, and the winning ticket is the one we hold. This response has serious problems. First, the multiverse has no observational evidence. No other universe has been detected. The proposal is unfalsifiable. No possible observation could disprove it. By the standards of the scientific method that the multiverse advocate is supposed to be defending, the multiverse is not a scientific hypothesis. It is a philosophical move designed to avoid the conclusion that the universe is finely arranged. Second, even granting the multiverse, the mechanism that generates the universes would itself require explanation. The problem of fine-tuning has not been removed, it has been multiplied. We now need to explain not only why our universe has the parameters it has, but why there is a universe-generating mechanism at all, and why that mechanism produces a distribution of parameters at all. The accusation often leveled against the theist is that they invoke a god of the gaps, that they fill in their explanatory holes with a divine cause. But what is the multiverse in this context, if not a naturalism of the gaps, an unfalsifiable entity invented specifically to avoid the conclusion the evidence suggests? The materialist, who refuses to invoke an intelligent cause on the grounds that it cannot be empirically demonstrated, then invokes infinitely many universes that have never been observed, has not improved his epistemic standing. He has merely chosen which kind of unobserved entity he is willing to accept. The third claim to examine is the one most often produced by popular commentary on cosmic topology and reflection physics. It goes something like this. If space is multiply connected, or if the universe has a CPT partner, or if the mirror sector exists, then human uniqueness and purpose are illusory. The reflection shows that the visible world is not special, that consciousness is just an accident of one sector among many, that meaning and purpose are projections we layer onto a cosmos that is structurally indifferent. This claim does not actually follow from any of the reflection models. None of the technical papers makes this argument. It is a metaphysical extrapolation imported into the science from elsewhere. Let us examine why it does not survive scrutiny. Consider what the cosmic topology proposals actually claim. They claim that the same primordial structures may be observable along multiple lines of sight because space wraps around on itself at a scale comparable to the last scattering surface. The claim is about light paths in a finite, multiply connected space. It is not a claim about consciousness, purpose, or meaning. The repeated views, if they exist, are repetitions of cosmic structure, not repetitions of biographies. The relevant claim of cosmic topology is that the geometry of space could be globally finite. It says nothing whatsoever about the value of conscious life within it. Consider what the mirror sector proposals actually claim. They claim that the visible particle content of the universe could be one of two parity-related sectors. The claim is about gauge structure and particle multiplicity. It is not a claim that human consciousness is illusory or that human life has no significance. A mirror sector containing different particles, different chemistry, and possibly different structures does not, by its existence, diminish the significance of what exists in our sector. The mirror sector proposal is silent on the value of consciousness. It could not, on its own resources, tell you whether consciousness mattered. Consider what the CPT-symmetric proposal actually claims. It claims that the universe after the Big Bang is the CPT image of the universe before it, in a specific technical sense. The claim is about the structure of cosmological boundary conditions. It is not a claim that human consciousness is one accident among many. The reflection across the Bang is a mathematical relation between cosmic histories, not a metaphysical leveling of meaning. What we are dealing with when popular interpreters draw nihilistic conclusions from reflection physics is a category mistake. The technical papers describe possible structural features of physical reality. The popular interpretations import metaphysical claims about value, purpose, and consciousness, and attach those claims to the technical results, as though the results entailed them. They do not. The structure of physics does not, by itself, settle questions about meaning. Physics describes how the cosmos operates. It does not, in its own language, evaluate the worth of what operates within it. The deeper problem with the nihilistic interpretation is that it cannot explain the existence of consciousness in the first place. The reflection models, taken together, propose various structural features of matter, time, and space. None of them addresses how unconscious particles produce the subjective experience of being a conscious observer. Neuroscience, despite extraordinary progress in correlating brain states with mental states, has not closed the gap between physical processes and the felt experience of consciousness. The hard problem of consciousness, the question of why physical processes are accompanied by subjective experience at all, remains unsolved. If consciousness is merely an arrangement of unconscious particles, there is no reason it should exist as subjective experience rather than as functional behavior without inner life. Yet, here you are, watching this video, having an inner experience of watching it. The materialist explanation, which says that the inner experience is itself just an arrangement of particles, faces a self-defeating problem. If the inner experience is just particles, then the very claim, consciousness is just particles, is itself just particles, and there is no reason to take it as more than chemistry. The argument, when followed through, dissolves the conditions under which it could be evaluated as true. The reflection models say nothing about this. They cannot. They are theories of structure, not theories of subjectivity. To use them as ammunition against the meaningfulness of conscious life is to demand that they answer a question they were never asked. There is a fourth question to examine, and it concerns the responsible reading of evidence. How often, the question runs, do sweeping metaphysical conclusions get hung on models still awaiting positive detection? Consider what the people working on these problems actually say in their official reviews. The 2024 Particle Data Group Review, the standard reference assembled by the international particle physics community, states plainly that the fundamental makeup of the large majority of the dark matter is, as of yet, unknown. That is a remarkable sentence. After decades of theoretical work, billions of dollars of experimental hardware, and refinements in cosmological observation that would have been unthinkable a generation ago, the fundamental nature of most of the matter in the universe remains an open question. The review does not say that dark matter is mysterious in some peripheral sense. It says its fundamental makeup is unknown. The largest matter component of the cosmos is not understood at the level of identity. The Planck topology analysis is similarly direct. After examining the cosmic microwave background for the matched circle signatures predicted by simple compact topologies, the analysis reports that these searches yield no detection of a compact topology. The honest scientific reading is that one of the cleanest predictions of the cosmic topology proposals has been searched for and not found. That does not destroy the broader theoretical framework. It does limit what can rationally be concluded from it. The cosmologist Paul Davies, in a passage often quoted by both sides of this conversation, observed that we will never explain the cosmos by taking on faith either divinity or physical laws. The phrasing is philosophically loaded, and Davies is not a theologian. But the content of the remark is striking even from a cosmologist who is no friend of theistic conclusions. He is admitting that the laws of physics themselves cannot serve as a final stopping point. They are not the kind of thing that is self-evidently necessary. To say the universe is governed by these laws is not yet to have explained anything. It is to have described the operating manual without addressing where the manual came from. What does it mean that even working cosmologists, in their more candid moments, acknowledge that the laws of physics are not a final explanation? It means that the strongest version of the materialist line, the one that says the laws are simply there, the universe is its own answer and no further question can be sensibly asked, is not the position of working physicists at their most careful. It is the position of popular extrapolators who have stopped asking questions earlier than the science itself does. The science, when read in its own voice, leaves the explanatory frontier wide open. The popular interpretation pretends the frontier has been closed. Notice the inversion here. The accusation often leveled against the theist is that they retreat into mystery, that they invoke an intelligent cause precisely where physics has not yet supplied a complete account, and that future scientific progress will close those gaps. But what we find when we look carefully at the reflection of reality literature is something closer to the opposite. The materialist account retreats into structures it has never observed, mirror sectors that have not been detected, CPT partners across boundaries that cannot be reached, multiverses with no empirical signature, parameters whose narrowness is treated as a stipulation rather than a finding. The intelligent cause account does not require any of these unobserved structures. It points to features of the observed universe, its lawfulness, its fine arrangement, its consciousness-supporting precision, and asks what kind of cause could plausibly produce them. The honest scientific position is one of disciplined, partial knowledge. The reflection models are interesting and worth pursuing. They are not established. They have not solved the major outstanding questions of cosmology. They have, in some cases, sharpened the questions and reduced the available parameter space, which is a useful contribution, but they have not delivered the kind of positive evidence that would warrant the strong metaphysical conclusions sometimes drawn from them. I return to this point often, not because it is comfortable, because it is true. The careful reading of the literature is that none of the reflection models is empirically settled. The popular interpretation that draws naturalistic, anti-theistic, or nihilistic conclusions from these models reads them in a stronger sense than the technical work supports. The papers themselves are careful. The popular extrapolations often are not. What the evidence, when honestly assembled, actually points toward is a different conclusion. The universe exhibits law-bound structure at every level we can examine. The structure does not explain itself. It does not generate itself. It does not, in any of the technical models we have considered, dispense with the question of why such structure exists. Every reflection proposal, however elegant, sits inside a larger framework of laws, fields, and boundary conditions. The framework requires explanation. The explanation does not come from within the framework. When you ask what kind of thing could explain a law-bound, finely arranged universe, finely arranged across constants, parameters, and cosmological boundary conditions, only one kind of answer survives examination. The cause must be external to the lawful structure it gives rise to. It must be uncaused, because an infinite chain of caused causes never reaches the present. It must be capable of producing law-bound structure, which means it must be the kind of thing from which order can come. It must be capable of selecting among possibilities, because the laws and constants we measure could have been otherwise. The capacity to select among possibilities is what we call will. The capacity to produce ordered structure is what we associate with knowledge. The capacity to actualize the chosen structure is what we call power. A cause that is uncaused, that possesses knowledge of structure, that exercises will in selection, and that has the power to bring the chosen structure into being, that is the description of an intelligent cause. It is the conclusion the evidence points toward. Evidence is read without prior commitment to keeping the intelligent cause out of the picture. It is the conclusion that survives examination when the popular metaphysical extrapolations from the reflection models are removed. What does it mean that the evidence, examined fairly, points to an intelligent cause? It means that the physics we have surveyed, the parity violation revealed at 0.003 of a degree, the mirror sector proposed to restore symmetry, the kinetic mixing parameter pinned to a narrow window, the CPT-symmetric universe extending across the Big Bang, the cosmic topology constrained by Planck, does not eliminate the question of origin. It refines the question, it sharpens it. It exposes the explanatory costs of every alternative answer. And it leaves standing, as the most parsimonious description of why such a finely structured universe exists at all, the conclusion that an intelligent cause configured the structure we observe. This is not a leap. It is the conclusion the evidence most naturally supports when the evidence is read carefully and the metaphysical extrapolations are stripped away. The reflection models, considered honestly, do not show the universe is self-explaining. They show the universe is structured in ways that require explanation. The nature of that explanation is the question that physics cannot answer in physics' own terms, and the question that, when followed where the evidence leads, points to an intelligent cause behind the lawful structure of reality. Let me bring this exploration to a close. We began with a small disk of cobalt cooled to within 0.003 of a degree of absolute zero. We watched as that small disk overturned a centuries-old assumption about the symmetry of nature, the assumption that the mirror image of physics was physics. We followed the consequences. We saw how Li and Yang's proposal, confirmed by Wu, broke the naive mirror symmetry of the universe and forced theorists to ask whether a deeper symmetry could be restored at a hidden level. We surveyed 3 different proposals for what physics could mean by a reflection of reality. The mirror sector hypothesis of Kobzarev, Okun and Pomeranchuk, sharpened by Foote, Liu and Volkas, refined by Beregiani, and constrained by experiments from Lux through CMS to Atlas. The CPT-symmetric universe of Boyle, Finn and Turok, with its specific predictions for neutrino properties and the absence of certain primordial gravitational waves, the cosmic topology proposals of Cornish, Spergel and Starkman, sharpened by Luminet's dodecahedral suggestion and constrained by Planck to the point where simple compact topologies are ruled out below the last scattering scale. We saw what each model claims. We saw what each model does not claim. We saw that each reflection, if it exists, lacks an ordinary visible duplicate of any observer in our sector. The mirror sector contains other particles, not other people. The CPT partner is on the other side of the bang in conformal time, not somewhere you could go. The cosmic topology repetitions are repetitions of light paths, not of lives. The reflection of reality, as physics has gradually mapped it, is austere. We then examined the metaphysical interpretations sometimes drawn from these models. We asked whether reflection physics shows that no creator is needed. We asked whether the kinetic mixing parameter, finely poised in its narrow band, is merely a parameter to be measured or evidence of selection. We asked whether the CPT-symmetric proposal removes the question of origin or merely restates it. We asked whether reflection physics implies that consciousness and meaning are illusory. In every case, the popular metaphysical interpretation went beyond what the technical work supports. The reflection models describe structures within a lawful cosmos. they do not explain why there is a lawful cosmos. They presuppose the framework whose existence is the deepest question. When the framework is taken as a brute fact, the materialist position has accepted the existence of an unexplained eternal structure. When the framework is recognized as the kind of thing that requires explanation, the conclusion that the lawful structure points to an intelligent cause becomes, in light of the evidence, the most parsimonious answer. The evidence file contains a parity-violating weak interaction, a mirror sector that survives only with specific tuned parameters. CPT-symmetric extension whose predictions remain to be tested. A cosmic topology pushed beyond the last scattering scale. And a dark matter component whose identity remains unknown after decades of search. The materialist account that says the universe is self-explaining does not survive the evidence. The account that says the lawful structure of reality reflects the intention of an intelligent cause, possessing knowledge sufficient to configure the laws, will sufficient to select among possibilities, and power sufficient to bring the chosen configuration into being, does survive the evidence. It is the conclusion the data most naturally supports when the data is read fairly. If you found value in this exploration, in the willingness to follow the evidence where it leads rather than where convention prefers, consider subscribing. It helps these deep dives reach more curious minds. The reflection was real, but it was never yours. Physics may permit a double of reality without granting us a duplicate life inside it. The mirror survived, just not in the way our instincts expected. What science found was not another you, but another way reality could fail to belong to you. The reflection points outward, not toward another self in some hidden corner of the cosmos, but toward the one whose intention configured both the visible world and whatever austere counterpart it may possess. Good night.